Chapter 13, Exponential and Logarithmic Functions. Section 13.1, Exploring Exponential Functions and their graphs. So, a exponential function is actually, well, and logarithmic functions are examples of transcendental functions. So, let's recall, let's say, the power function. F of x equaling, let's say, x cubed. So this is an example of a power function. Now, and so the base here is your variable, and your exponent is fixed. For the exponential function, the base is fixed, and it's the exponent that varies. And so, in general, let b be a real number that's greater than 0, and let b not equal 1. Then an exponential function is a function of the form b to the x. So if let me look at the graph of an exponential function. Suppose here that we want to look at the graph of y equaling b to the x. In this case, b is greater than 1. Then it will look like this. It will always be increasing. So as you proceed from left to right, my y values are always getting larger and larger. It is also concave up, so it's increasing in an increasing manner. Um, Next, it has no, it has no vertical asymptote, but it does have a horizontal asymptote. The horizontal asymptote is just the x-axis. And it approaches this as x becomes smaller and smaller. um, and it crosses the x-axis. It does not cross the x-axis, so it has no x-intercept, but it does have a y-intercept at 0, 1. Next, oops. Next, suppose that we look at the graph of y equaling b to the x, and suppose that b is between 0 and 1, then this is always decreasing. It's still concave up. Um, we have a horizontal asymptote. No, I guess I should say no vertical asymptote. Asymptote. Oops. So I should say that also. So it's no horizontal asymptote. No vertical asymptote. And it has a horizontal asymptote. The horizontal asymptote of y equals 0 as x goes to positive infinity. So for very large values of x, it has no x-intercept. And the y-intercept is still uh, is at 0, 1. Okay. Um, so let's look at some examples. So on page 543, let's say problem number 2. F of x equaling 4 to the x. In exercises 1 through 28, sketch the graph of the function, give the coordinates of the y-intercept for each function, and the equation of the asymptote. Okay, so let's do that. So in this case, the base 4 is greater than 1. And so it's going to look like, well, this graph. And so let's do that. So at 0, well, at negative 2, it's 1 over 16. Negative 1, 1 over 4. 0, 1, 1, 4. And so it looks something like this. The x-intercept is at the point 0, 1. The equation of the asymptote is y equals 0. Let me do problem number 4. F of x equals 2/3 to the power x. And so We have something looking like this. So y equals 2/3 to the power x. So at -2 is going to be 4/9. At -1, it'll be 2/3. Sorry. At -2, it'll be 9/4. And so just a little bit over 2. At -1, it'll be 3/2, so 1.5. At 0, it's 1. At 1, it's 2/3. At 2, it's 4/9. And so I have here the asymptote is y equals 0. And so it just looks like this graph here. Let me do problem number 12. F of x is equal to 4 to the x minus 1. So this is just a translation of, well, actually, let me do this first. Let me write f of x as y. And so I'm supposed to translate y equaling 4 to the x. And I'm going to translate, since I'm translating the x, and it's a negative x, I'll go in the positive x direction, 1 unit. And so I'll go right by 1. Okay, so let's do this. So, maybe I'll graph y equal f of x. I'll graph the y equal 4 to the x. Oh, it goes up much faster than that. It's this guy. So let me graph this again, so it looks a little nicer. Okay, that looks a little better. So let's try to graph this. That's a little better. So this is a graph of y equal 4 to the x. So at 1, it's got to be 4. It should go faster than that, but and now let's translate this over 1 unit. So if I do that, it'll look something like this. So this is the graph of y equaling 4 to the x minus 1. Okay, so obviously the asymptote is still y equals 0. And this is because as x gets very, very negative, then 4 to the negative power is obviously going to be very, very small. It'll go to 0. Let's try to find the x-intercept. Y-intercept, sorry. There's no x-intercept. The y-intercept. So for the other ones, I mean, I could have done this, but I'll do it for this particular one. Let's find y equal 4 to the, well, to find the x-intercept, you replace place x by 0, solve for y. And so you get y equals 4 to the negative 1, 1 over 4. Therefore, the y-intercept is at 0, 1 over 4. And that's your y-intercept. Let me do problem number 20. F of x equals 3 to the x plus 1 minus 2. Okay, so let's replace f of x by y, and let's add 2 to both sides of my equation. So I get y plus 2 equals 3 to the x plus 1. And so I should translate the graph of y equaling 3 to the x. In this case, it will be to the negative x direction by 1 unit. So to the left by 1. And I'll be adding 2 to the y, so I'll go in the negative y direction, so down 2. So let's graph this. Okay, so let's do that. So let's graph y equal 3 to the x. So it goes up. Oops. Like this. And let me change that color. Let's change that to a red, I guess. Okay, so there. Let's go to the right, left by 1. And down 2. Okay, so let's do that. So that means that I'm going to be taking this. Actually, why don't I just draw the, since I'm going down 2 units, I'll draw the x-axis, being translated down by 2 units, so it'll make it easier for me to draw. And so move this down 2 and over 1. So basically, so the x-axis is going to go over 1. So now let's try to graph this. So at 1, it should go there. Okay. So it should look something like. The fact that it intersected there at 1 is just a coincidence. I didn't actually mean it to do that. We'll actually have to see where it intersects, because it seemed to have naturally done that. I don't think it actually does. Okay, so let's take, well, if I look here, what's the asymptote? Well, it looks like the line y equaling negative 2. Since we translated down the x-axis by 2 units, that and the horizontal asymptote was the x-axis for this red curve, then for the curve we want, the black curve, the graph of y equaling 3 to the x plus 1 minus 2 is compared to the graph of y equaling 3 to the x. Oh, by the way, did I? Yes, I did draw both those. And so let's determine the y-intercept. Okay. And so replace x by 0. Let's see what happens. And so we have here 3 to the 1 minus 2, but 3 to the 1 is just 3 minus 2 is 1. So no wonder it looked like it went through that point, because it actually does. And so the y-intercept is actually the point 0, 1. It's actually the same point. Okay, so let me do problem 24. But before I do problem 24, let me give you the value e, the number. So let's recall something first, I guess. Recall. 1, 5. Those are just symbols for numbers. 1 is a number, 5 is a number, pi is a number. And similarly, e will be a number. And e stands for a number. Also stands for a number. A real, well, actually, it's a real irrational number. For a number, it will be, in fact, an irrational number. Just like pi is an irrational number. So, I'll give you some differing ways to look at the number e. So I can think of e as just being 1 plus 1 over 1 plus 1 over 1 times 2 plus 1 over 1 times 2 times 3 plus. So if you keep adding these all up, and you keep doing it 1 plus 4 times 3 times 2 times 1, 5 times 3, and you keep adding up all those forever, then you get the number e. Similarly, e, well, let's write it this way. If I take 1 plus 1 over x and raise it to the power x, then as x gets very large, we approach that number e. So 1 to the, so let's say 1 plus 1 over a million to the power of 1 million will be very close to e. Make it even bigger. 1 plus 1 over a billion, all to the power of 1 billion, will be very close to the number e, even closer, etc. And so pick larger and larger and larger and larger numbers, and you get the number e. Similarly, if you take the xth root of 1 plus x, then this also becomes very close to the number e. Okay? So the millionth root of 1,000,001, etc. Okay? Next, if I look at the graph of let's say um, y equaling 1 to the x, well, it's always equal to 1. Y equaling 2 to the x, y equaling 3 to the x, well, and we look here at the point 0. If I look at these, if I look really close, then very close to the point x equals 0, it looks like a line. The line that it looks like will be called the tangent line. The line that just intersects that curve at that one point. And you notice that it has a slope of 0 here, then it's a fractional slope, and it looks like a slope that's bigger than 1, etc. And so eventually there will be some line where the slope of this tangent line is 1. And so let's look at, let me graph this again. And so if I look at the tangent line, so this is y equaling e to the bx, then this is the tangent line to this curve. So the tangent line is, I can say several ways. It's the best linear approximation to the curve. It's the line that touches line touches curve at one point, curve at that one point. Okay. And so E is that B such that the tangent line to y equaling b to the x equals 0, has a slope of 1. So whatever value, so notice that, obviously if I have y equal 50 to the x, it'll go really, really steep. And y equal 1 to the x, well, it has no slope, it has a slope of 0. So somewhere, for some value, I'll have that this has some sort of slope. And so I call that value of that base the value E. And so that's how I define E. Another way is, well, just to say it's whatever that number is. So another way to say it, I guess, is that E is approximately, I guess we can plug it onto a calculator. Here, wait 1 second. Let me get a approximate value here. And so it is approximately, I guess I'll write a few places. Um, so E is approximately 2.1, 2.7, 1828, 1828, 182, 4590, 45235, 36028, etc. We can keep going on and on forever. So as you keep, obviously it does not end and doesn't have uh, it doesn't end in any sort of, with any sort of pattern or anything. Okay, so just notice that it's some positive number and it's some positive number greater than 1. So it means that the graph of it will look like this because E is greater than 1. So it looks something like that. And so let me do problem number 24. F of x equals e to the 2x. And so this is the same as y equaling e to the 2x. So we can think of this as y equaling e squared to the x. E squared, well, if e is around 2, then obviously e squared is going to be some number greater than 1. It's going to be something like, 6 or something or 7. And so, since the base is greater than 1, then it's going to look something like this. So this is a graph of y equals e to the 2x. Of course, the horizontal asymptote is just y equals 0 and intersects at 0, 1. Okay. So that was 1. Okay, I think that might, well, actually, let's check it there. Let's go to the next page. I guess that's it for section 13.1. So let me end this.